Hi there. In this video, we're going to finish up what we're working on in Chapter 9, and we're going to look at separable equations. These are differential equations, so let's get started. So the idea is that if a differential equation is separable, then we need to be able to write it as a function of x times a function of y, or a function of x divided by a function of y. And we have to be able to solve for the derivative. So not every differential equation is separable. It's a very small group that are, but that's what we're going to look at. So you want to look for one of these two forms, and I'll show you how to do that in the first example. The way we solve something in this form, so you always get it in this form to solve it. You basically cross multiply. So dy, whatever's on the top has to stay on the left side. So you multiply by h of y, multiply by dx, and you end up with this. And then you just integrate both sides. Once you've done the integral, solve for y if you can. If you can't solve for y, that's okay. You can just leave it the way it is. But all the ones we're going to see in the video today are solvable for y. All right, so here's our first one. So the derivative is x squared times y squared. So what that means is that you just plug in the coordinate of a point on the graph, and the slope of any equation, of any solution that passes through there, has to be the x coordinate squared times the y coordinate squared. So it's pretty easy to understand, but that still doesn't tell us how to solve it. So we have to get this in the form of a function of x divided by a function of y. So the easiest way to do that is just rewrite this as a negative exponent. There's no other way to do this problem. This is how you have to do it. Now you can see that we have a y in the denominator, so you can cross multiply and then integrate. It's the way it always works. So you always get the y in the denominator. Whatever's on top over here, you get it on the bottom over here. And both of these are power rules, so they integrate pretty nicely. Then I'm going to rewrite this algebraically as 1 over y and multiply both sides by -1. You always want everything on the right side. All constants go on the right. You need to get y by itself on the left if you can. So here we can. And that's the answer. But notice I didn't circle it. Because if you look at this, and then you look at the original equation, this is a solution, right? This is an infinite number of solutions, actually, because of the plus c here. But you can see that if you plug in y equals 0 here, 0 times whatever is going to be 0. So the line y equals 0 is also a solution. And this is not immediately obvious, maybe, but if you look at this equation, this thing can never be 0 because the numerator has a 1 in it. So that means you need to show that there's an additional solution. And these are called constant solutions. They pop up all the time in differential equations, and you always have to look for them. We saw some in section 9.1 with the population model, where we had the equilibrium solutions. Turns out those are also constant solutions. And if you're not sure if there's a constant solution, the best thing you can do is just graph the differential equation, the slope field. And if there's a constant solution, you'll see it because it'll just be a horizontal line. So I went ahead and plugged in some values here just to see what it looks like, and I saw that y equals 0 popped out as a solution. So it turns out you have to include both as your answer. So this is very common. So if you forget to check for constant solutions and you type in this function as your answer, it'll be wrong. And it's sometimes hard to see constant solutions. So the graphing option is always very good. And you're allowed to use it. All right, let's keep moving. So now we're going to look at an initial value problem here. So as you recall, the way this works is this gives us a slope field And this gives us a curve that passes through a single point. So you solve this first, then you plug this in. Okay, so the way that I'm going to do this, again, you have to solve for y first, right? Or sorry, you have to solve for y prime first if you can, because that tells us what form to put the right side in. So I subtracted y from both sides. Then I rewrote y prime as dy dx. So I need all the y's on the left side and all the x's on the right. So the way to do this, I have an x on the left here. I don't want it on the left, so I multiply by 1 over x on both sides. That'll cancel the x over here. It'll put an x on the right. So I definitely want that. And you can see on the right side the same thing's going on. I have y's over here, but I don't want them on this side. I want the y's on this side. So I'm dividing by this thing too. It'll cancel here, and the y terms will appear on the left. Right? So it simplifies real nice. And then I just multiplied both sides by dx. Oh, I shouldn't be there yet. And then we just integrate, and the left side, obviously here, you solve it with partial fractions, as you can see. And then the right side is just a normal integral. So make sure you can do the partial fractions here. I'm not doing it in the video. I'm trying to keep the videos sort of short if I can. And from here, our goal is to solve for y. But we have two different y's. You can't solve for y if you have two different y's. So combine that into a single log using log rules. And in the next step, I'm going to rewrite the log as an exponential. So this is something you absolutely have to be able to do. It pops up absolutely all the time in this section. And so if you want to think of it as just take both sides and make them powers of e, that's one way to think of it. So that's how I wrote it. Right? So this is here's the left side, here's the right side. I just made them exponents of e. And then you can see that this right side, this addition, just turns into multiplication. And what we're going to do is we're going to assign the letter k to e to the c. And then use the cancellation rules, right? E to the natural log of anything is just that thing. And then we're using this. E to the c becomes k. E to the natural log of x becomes x. So those both have absolute value. But because we're doing an initial value problem here, you can drop the absolute value. Because solution curves cannot intersect. So I dropped the absolute value, multiplied both sides by y. I switched the kxy and the 1, right? I subtracted on both sides and then added on both sides. Then you factor out y on the left and divide by what's left over, and you get 1 over 1 minus kx. So this is the general solution. So this tells us the slope field, what it looks like. But we have an initial condition, so we want to plug it in. And I'm going to plug the initial condition into this equation here, because I'm trying to solve for k. It's a lot easier to solve for k in this equation than this one. Right, so I just plug it in here. And it turns out that because when I plug in both values, it's positive on both sides. Again, I don't have to use the absolute value, which is nice, so I just dropped it. So I get k equals 2, and then you plug k equals 2 in here, and that's your answer. So this is, again, pretty typical problem of its type. There's always one step of calculus in all the problems in Chapter 9, and the rest of it is just a bunch of algebra. So that's just the way differential equations goes. And here's what the graph looks like. Right, you can see it's a real weird looking slope field, but that's okay. They don't have to look like any particular thing. And you can see that there's exactly one curve through that point. Alrighty. Let's keep going. So this is the problem that I talked about in the previous video. That I said we would solve it in this section, and here we go. So the way you do this is you have y prime equals x plus y. This is not separable, right? Because we have a plus here. But we can make a change of variable. And when we do that, it becomes separable. So it's a little algebra trick we use so that we can do calculus. So this is the way I did it. I went ahead and subtracted x from both sides. I want to get y by itself because in the original equation there's a y prime. So I want to get y by itself and then take a derivative. So subtract x from both sides, take the derivative. So we're taking the derivative with respect to x. So this becomes u prime, this becomes 1, this becomes y prime. Now I plug everything into the original equation. So y prime is u prime minus 1, and x plus y is u. So here I get u prime minus 1 is u. Now this might not look separable, but it is. Because if you rewrite u prime as du dx, now you can see we only have 3 things that we have to manipulate instead of 4. So I add 1 to both sides. And when I do that, you can see that du is on the top over here, so I want all the u terms on the left, so I just divide by u plus 1. And then multiply both sides by dx. And now it's separated. So you don't need to do a substitution here, right? I mean, you can if you want, but there's no reason to do it, right? This is just an ordinary integral. So this right side's going to be x. Left side's going to be natural log of u plus 1. Again, we put the absolute value here, but as soon as we go to solve for y, we drop them. Now I use the exponential trick that I had before. So I'm going to write these as exponents on e. So you're going to get an e to the x here. E to the c turns into k again. And on the left side, we just get u plus 1. So same trick we used in example 2. And then you just back substitute, right? We have u as x plus y. Just plug that back in. And now we can solve for y. And you're done. So what we saw in section 9.1 when we were solving these, I gave you this equation and we did an initial value problem. Here we're solving. So it's a little bit out of sequence, but at least you've seen how to do a problem all the way through, right? Solve it, plug in the initial condition, check your answer with a graph. So we've done all that stuff. Again, the check for this is in section 9.1, so I'm not doing a graph. All right, last thing we're going to talk about are what's called mixture problems or mixing problems. The idea is that we have a tank that's full of some substance, and it could be salt, could be beer, whatever. And then you have a pipe bringing in a different mixture. And when the pipe brings in this other substance or a different concentration of the substance, it changes the concentration in the tank. And then it's mixed, and there's another pipe that brings the mixed solution out. So the amount of the quantity in the tank is changing all the time. So the way we set these up is you always set y, so your dependent variable, always set it equal to how much of the substance is in the tank at a given time. Then the derivative is the rate at which the substance is being added minus the rate at which it's being removed, because there's some coming in, there's some leaving. And it turns out that when we set these problems up this way, you usually get a first order separable differential equation. So let's see how to do one of these. So you have 500 gallons of beer, and there's 4% alcohol by volume. And then we have beer with 6% alcohol is pumped into the vat at a rate of 5 gallons per minute, and the mixture is pumped out at the same rate. What is the percentage of alcohol after 1 hour? So again, the way we do this is we're going to set y equal to the amount of alcohol in the vat at any particular time. So that's the first thing we do. Right? So it's in the vat. And we're given that the initial condition that there's 500 gallons and it's 4% alcohol. So there's 20 gallons of alcohol to start. And we want to find how much is left 60 minutes later, right, when the mixture comes in at 5 gallons a minute. Sorry, the 6% alcohol comes in at 5 gallons per minute, and then the mixture leaves at 5 gallons per minute. So the rate of change of alcohol volume in the vat is given by, so the derivative, right? So y is the amount of alcohol, t is time, and it's a positive number. The rate in, right, is adding alcohol, and the rate out is removing alcohol. And so we just build an equation. So how fast is the alcohol coming in? Well, it's coming in at 5 gallons a minute, and it's 6% coming in. How fast is the alcohol leaving? Again, 5 gallons a minute. So, but the concentration is the amount of alcohol divided by 500, because there's 500 gallons in the tank. It doesn't change size. So you take the amount of alcohol divided by 500. And you can see that to start, this makes sense, right? Y of t at the beginning, there's 20 gallons of alcohol here. 20 divided by 500 is 0.04. So you can see that at the very beginning, this makes sense. But a higher concentration of alcohol is coming in, so eventually the amount of alcohol is going to go up. All right, then you just simplify this, right? So 5 times 0.06 is 0.3. 5 divided by 500 is 1 over 100. And I just dropped all the units. You don't need the units. When you're building this thing, it's good to have the units in there. It'll help you with dimensional analysis. Then what I did on the right side is I factored out whatever number is times y of t you want to factor it out. The reason is this is going to be a constant on the right side when we set up our equation. And with this inside, there's no chain rule. I mean, there's a negative, but negatives aren't hard to deal with. There's no number chain rule. So when we do the integral, we have less to think about. It's just much easier. So this is the way I suggest doing it. Everybody does this a little bit different. The answer key might show something slightly different. But this is the way I recommend doing it. To me, it's very easy. Then it's a separable differential equation, right? So the number stays on the right, divide both sides by this, multiply both sides by dt, and then integrate. And you can see what's going to happen, right? This is just going to be 1 over 100t plus c on the right. On the left, this is just a natural log of this, but because there's a minus, the chain rule and the derivative gives us a minus, so we have to include a minus. So it's negative ln of 30 minus yt. Over here, we knew we were going to get this, right? Just doing a simple integral. And as we've seen for the last 3 consecutive problems, we have a natural log on the left and some sort of plus c on the right. So when we do e to the power of both sides, you can see that this e to the c is going to turn into a k again. And then I multiplied through by a negative. So this k will be negative, and it flipped the sign on the 30. So just to get you all caught up, I subtracted 30 from both sides here, but there's a negative out front of yt, so I just multiplied through by a negative. This constant absorbs the negative. In fact, you'll see later when we solve for k, we get a negative number. And it flips the sign here. So that's 2 steps in one. You can do it as a single step. All right, now we plug in the initial condition. So 20 is ke to the minus 1 over 100t plus 30. And you can see that when we plug in 0 here, this whole thing becomes 1. So k plus 30 equals 20, so k is negative 10. And so I just plugged in k is negative 10, and then I just switched the sides. And that's the equation. But the question, so that would solve it if we were just stopping there. That'd be the equation for how much alcohol at a given time. But we want to know how much is left after 60 minutes. So we plug in y of 60, and you get 24.5 gallons of alcohol. But the question isn't asking for how much alcohol. The question is asking what's the alcohol percentage. So we have to divide this by 500 to get 4.9%. So as you can see, a lot of the problems in this section look very similar. Make sure you can do all the problems in the notes. As you are well aware at this point, that's the kind of stuff that shows up on tests. And that's it for this section. If you have any questions, let me know. And next video will be chapter 10. So that's it for this video. See you guys later. Bye-bye.